Okay, pre-calc. So first of our videos about partial fraction decomposition. This is case 1. We're going to explain briefly each case and then how to solve one that is case 1. So you'll see the 4 different cases are listed. We have what are called distinct linear factors, repeated linear factors, and then distinct irreducible quadratics and repeated irreducible quadratics. Okay, so the basic idea of partial fraction decomposition means rewriting fractions. We're unsimplifying things in a lot of ways. It's kind of like how factoring and distribution are opposites. So if we think of 5 over 12, we could write it as something like 4 over 12 plus 1 over 12, or we could have also maybe thought 2 over 12 plus 3 over 12. But the idea with partial fraction decomposition is if we take something like 5 over 12 and we write it in a way so that our denominators are not 12. It's not as easy then. Like if we say maybe 4 and 3. Well, in this case, if we did something like partial fraction decomposition, we'd end up with negative 1 over 4 and 2 over 3. And the reason for that is that if we took the opposite way and looked at these two fractions and tried to combine them, we'd first have to create common denominators. So we'd multiply this by 3 to create a denominator of 12, and so the top would be multiplied by 3, multiply the second equation by 4 over 4, and we'd end up with 8 over 12, and that gives us our 5 over 12. So you see, by using what partial fraction decomposition is, we're going to end up with these two fractions to get 5 over 12. Okay, now this really has a lot of implications in calculus, and we talk about this a lot when we start doing integrations, and sometimes the only way to integrate something is to actually separate it into two things by doing partial fraction decomposition. Okay, so we're going to do this on rational functions, hence the fraction that we just talked about. And every rational function is just going to be some function p of x over another function q of x. It could be as simple as 2x plus 4 over 3x cubed minus 2x plus 1. Okay, that would be a rational function. Something we talked about way back early at the beginning of the year, and we did a lot of graphing with these, and we talked about asymptotes and holes and that kind of thing. Okay, so every q of x, and you notice now we're talking about our denominator that we're going to look at, is always going to be able to be written as a set of linear factors or what are called irreducible quadratics. Now, irreducible quadratics could be something like x squared plus 2x plus 3. Okay, and it's considered irreducible because there's no way to factor this without using irrational numbers or have imaginary solutions. This would be unfactorable. So the factors of q of x will reduce into our 4 cases like we just talked about. We can either have non-repeated linear factors, meaning every factor that we create is distinct, it's not repeated. We could then also have repeated linear factors, which changes the process just a little bit. Or we could have a combination of linear factors and non-repeated irreducible quadratic factors. And the last one could be repeated irreducible quadratic factors. So really this is a hierarchy. Even with our repeated irreducible quadratic factors, we could actually also include the non-repeated or even the repeated linear factors. So as we go down, we just kind of get a little more complicated, a little more detailed with our solution. The steps for case 1, and really going to be the same steps for each one, they just get a little more complicated when we start talking in particular about 3 and 4. But if case 1 is only with repeated or non-repeated linear factors, a non-repeated linear factor could be something like ax plus b, like you could have x plus 2 and x minus 3. I mean, each linear factor is distinct. Okay, the steps for this, we're going to have several, but they're not that complicated. The first one, we need to be able to factor our denominator completely, so into a combination of linear or irreducible quadratics. Then we're going to set up the PFD by using A, B, and C, and I'll show you what that means. You're essentially going to have an equal sign. Each linear factor is going to be a denominator with A, B, or C as the coefficients of your numerators. Okay, you're going to multiply both sides by the LCD. We remember LCD is lowest common denominator. That's going to be whatever your factored form was. The LCD is really just q of x. And what that does is eliminates the denominator. So our denominator is going to cancel out when we do that. Okay, after we've done that, now we're just going to have an equation with several different variables, and we're going to simplify that. You're going to need to distribute and combine like terms. after we do that, we equate the coefficients, meaning you're going to take, if you have x squared terms, you're going to take all of your coefficients of your x squared terms, add them up and set them equal to some number from p of x, and then you can take all of the coefficients from your x terms, add them up and set them equal to the coefficient from p of x, and then all of your constants and add them up and set them equal to the coefficient or the constant from p of x. Doing that is going to create a system of equations with however many variables determined by our A, B, C, D, however many we had up there. And finally, once we do that matrix, we are just going to use our calculator to solve that matrix. That's one of the big reasons we did that and why we have talked about systems so often recently. And finally, substitute the values for A, B, and C back into the PDF, meaning write your numerators, these are the numerators, to show what your actual answer is. Okay, these are the values we're looking for, but your actual answer is when you substitute them back in. Okay, hopefully one example is going to make that a little more clear. So we have x over, and what I want to do first is factor this denominator. Now be careful, x minus 2 times x minus 3. That's my factor denominator. Okay, step 2, we need to set up our PFD, meaning each one of these factors, so since we have two factors here, I'm going to write two fractions, and our factor goes in each fraction. When we talk about just a linear factor, we just put A and B here. Okay, we don't have a third, so we don't need C. If we did have a third factor, we'd have plus another one with C over that third factor. Okay, next thing we do is multiply by the LCD. So that means that each one of these fractions is going to be multiplied by x minus 2 times x minus 3. Remember, the q of x, whatever your denominator here is your LCD. And when we do that, this should eliminate all denominators. So the x minus 2's cancel out over here, and the x minus 3's cancel out, and we'll just end up with x. Equals, here our x minus 2's cancel out, so we have a and then times the quantity x minus 3, plus, last one, the x minus 3's cancel out, and we have b times the quantity x minus 2. Okay, next piece was then to simplify this side, so we need to distribute. Start by distributing. We're going to have ax minus 3a plus bx minus 2b. Okay, we can then do what is called equating coefficients. So I'm going to go ahead and add a 0 here, and you'll see why I'm going to do that in a minute. If I equate coefficients, meaning I'm going to make an equation, I have a 1 as my coefficient for x, I have an ax and a bx, which means the only way to get 1x over here is if a plus b add up to 1. So we know they're both going to need to be fractions or a positive and negative. The next thing I'm going to do is then all my constants, which is why I wrote this 0 here. So my constants are anything without an x variable. It may have an unknown of a, like here my constant is negative 3a, or b, here my constant is negative 2b, but that doesn't mean that they're not still constants. There is no unknown variable x. So if I equate those coefficients, I now get 0 equals negative 3a minus 2b. And the other thing I'm going to do is turn these equations around. No particular reason other than I'm going to create a matrix with them now, like we were talking about late last week. So we had 1, 1, and 1 would be the first row. Negative 3, negative 2, and 0 would be your constant for that one. So we have your A column, your B column, and your constant column. And if we solve this matrix, we go ahead and plug that into our calculators, we would get that A is equal to 0.4 and B is equal to 0.6. And so we're ready then to rewrite our answer. If we go back up the top, A is 0.4, B is 0.6. That means that this problem will break down to be 0.4 over x minus 2 plus 0.6 over x minus 3. And that would be our partial fraction decomposition. Okay. One more quick example. I'm going to go through it a little quicker just to help you. So we know this numerator is going to factor into x minus 4, x plus 2. So I'm looking for something x minus 4 and x plus 2. So we're going to have an a and a b. If I multiply through by my LCD now, I'd end up with x equals a times x plus 2 plus b times x minus 4, and distribute those values, ax plus 2a plus bx minus 4b, and I can then go ahead and equate coefficients. So I'm going to have 1 equals a plus b again. That's just a coincidence. It's not always going to be that way. Remember, we're going to have a plus 0 here for our constant, so 0 equals 2a minus 4b. I'd create my matrix, and I could plug that in. If I created my matrix and solve, I'm going to get that a is 0.67 and b is 0.33. Okay, so I went through that one really quickly. But essentially what I did was I factored this left side in x minus 4 and x plus 2. So that tells me I'm going to have two fractions because I have two factors. So a over x minus 4, b over x plus 2. When I multiply both sides by this, the x minus 4's, x plus 2's cancel out on the left side. On this one, the x minus 4's would cancel out, so I would have a times x plus 2. The second one, the x plus 2's cancel out, so I'd have b times x minus 4. I then distributed the a, distributed the b, that's how I got here, and then I equated coefficients. So x, ax, and bx, and then my constants, 0, 2a, and negative 4b, and I could create a matrix, use a calculator to solve that. I'd get a is 0.67 and b is 0.33. So that tells me that I'm going to get 0.67 over x minus 4 and 0.33 over x plus 2. And that would be my partial fraction decomposition. Okay, this will definitely be the longest video of the 4 cases because I don't need to introduce the other 3 types and what partial fraction decomposition means. So the next ones will be a lot shorter and hopefully a little bit easier. Big thing is we're going to need to practice on factoring, and we're trying to rewrite fractions as a combination of 2 different fractions. Okay, see you next time.